Hi, this is Peter Orr from Intuitive Analytics, and I'm fortunate to have with me my colleague here, Dr. David De La Nuez, who received his PhD in Operations Research from Columbia. Now, Operations Research is at its core a lot about optimization, isn't it, David?
Absolutely, Peter. That's what got me into OR in the first place.
All right. And I'll embarrass you a bit here. Weren't you the first and for many years the only one in the engineering school to win a President's Award for Best Teaching?
You know, Peter, engineers get a really bad rap for teaching. There are some good ones out there, and some folks thought that I was one of them. And yes, you have embarrassed me. I did get an award just like that some number of years ago.
All right, congratulations. Well, we're going to be doing some teaching here today. No pressure, David. But in this third video in our Propeller Head series on bond structuring, we'll expand on the linear algebra and intro to bond optimization that we've done before. And you can find those videos over here on our resources area of our website, intuitive-analytics.com. And you can see here that we've sorted these videos by level, and the Propeller Head video, the first one on linear algebra and bond structuring, and the second one on optimization and bond structuring. Both pretty short, pretty compact, but they lay the foundation for what we'll go through here today. And so what we'll cover today are, first, optimization visually. We'll talk a little bit about what optimization is, again, on an intuitive level with a pretty picture. Then we'll move into actual bond structuring as linear programming and how to set up and define a linear program to solve a bond structuring problem. And then last, we'll give an industrial example, at least talk about one, again, using a nice visualization of a linear program that solves a bond structuring problem. So with that, we'll move right into the first section. So here we have a function of x, and x is ranging from -10 to 10 on the horizontal axis. And probably without a whole ton of difficulty, you can see that our function of x is actually just x squared. You can see at -10, our value for f of x is 100, and at +10 also our value for f of x is 100. The nice thing about this function is it gives a very simple intuitive minimum. At the value of 0, where x is 0, our f of x value takes on its minimum value of 0 as well. And the reason we use this function is to be able to talk about when you're doing bond structuring, there is something that is called an objective function. The objective function being the thing in optimization that you're trying to minimize. So in public finance circles, often it is desirable to minimize something like a cost of capital or a true interest cost, or maybe an all-in true interest cost. And that is effectively a yield calculation that allows you to get back to a target par amount of bonds with some adjustment based upon present valuing debt service payments on the bonds. And so the TIC could be a function that you're trying to minimize. Other functions that you might try to minimize or maximize for that matter might be present value of debt service. If you're a borrower, that seems to be a noble goal. You might also try and maximize present value savings. If you have some function that defines present value savings, you might want to maximize that.
Or if you're a banker, Peter, you may want to try to maximize the size of the refunding.
You could want to maximize the size of the deal. That is another objective function. That's exactly right. Thank you. So what often happens in public finance is that the constraints on the specific variable in question, and as I've said, we've only got a single variable here, x, are so tight that there's not really a whole lot of optimization happening. You can see in this particular case, we've specified that x needs to be equal to 7. And if x is equal to 7, then clearly there's only one value for our f of x, 49 namely, and there's not a whole lot of movement that can happen along the objective function itself. Now, if we think of x a little bit more broadly, and perhaps we've got an x that is representative of a particular principal payment in a given year. Maybe an issuer has some flexibility about how much principal is repaid in, say, year 3 of a financing. If there's some flexibility there, well, then there actually is something really to optimize over. We can get to a minimum or a maximum point, depending on what we're trying to achieve. Obviously, in this particular case, our minimum point is going to be at x equals 3, where our f of x is valued at 9. But this is really just to give a sense that to the extent that you've got some flexibility in your optimization problem, this allows for a much more powerful way to construct and ultimately solve for what the issuer's true goals and constraints might really be. And that's one of the things that we're going to be talking about here in these videos as we go forward. Anything I missed or left out, David?
I don't know, Peter. I think you're headed for an A in my class.
Outstanding. So moving on from this simple graphic, we'll go into part 2 of this presentation. And here we've got the same information that we showed on those prior videos that explain linear algebra and very basic optimization. But we're just going to take an example here where we've got 3 bonds, just 3-year structure, 1, 2, and 3 years, and they have annual coupons of 3, 4, and 5%. And what we did in those prior videos is say that our A matrix, in order to come up with the debt service calculation that we want in public finance, is going to be reflecting the cash flows per dollar of bond that occur in each column. So bond 1 is going to have the cash flows for the 1-year bond at 3%. Bond 2 will be the 4% bond over 2 years. And then bond 3 will be the 5% bond over 3 years.
That's really the key in what we're going to build here, Peter, is that we need to think of the cash flows in terms of per dollar.
Got it. So moving into what a linear program is, I'm going to hand this over to David because he clearly is the expert and will stand down.
Thank you, Peter. So the general form of a linear program that we're looking at here is to minimize a linear function, and you can write a linear function as the product of a vector of coefficients, that's C transpose here, times a vector of decision variables. And decision variables are what you're trying to come up with. In our case, principal amounts, for example. Now, what you're trying to do is, as we saw in the previous slide, you're trying to find a minimum of your function subject to a certain number of restrictions or constraints. In its most general form, linear program constraints can take the form of any number of inequalities, written here as ax smaller or equal to b, as well as any number of equalities, written here as a eq equals b eq, as well as what are also linear restrictions on the variables themselves, the x variables. Each variable can be bounded from below or above by a number as well. So, for example, in the second year of your bond structure, you can have no more than $10 million of principal. So let's move on to actually building a linear program. It's often helpful to think when you're modeling a linear program in terms of equations before you make the leap to manipulating larger structures like matrices. So here we have an arithmetic representation of what we were talking about before. In the first row you have the total debt service due in the first year. In the second row you have the debt service due in the second year, and in the third row you have the debt service due in the third year, much like we had done in a previous video. Now, suppose you're looking for level debt service. How do you achieve that in an equation? What we're doing here is a nifty little modeling trick from linear programming and optimization in general. We're going to have a variable measure what the level of your debt service is. We're going to call that variable L. And in order for L to take on the meaning we want it to take, we're going to subtract it from each of the debt services in each of the 3 years and set that quantity equal to 0. So if you want to, you can think about it as using your 7th grade algebra, move the L over by adding it to both sides of each equation, and you end up with L is equal to the debt service in each of the 3 years. So if you can find a solution to this system of equations for x1, x2, x3, and L, all 4 variables, that satisfies all these constraints, you'll have level debt service.
But David, we've got 3 equations and 4 unknowns. Now, going back to my junior high algebra, that was going to not get me a solution that I would be happy with.
Peter, it's not uncommon in linear programming. In fact, linear programming industrial examples will have many more variables than rows. And the classical algorithm for solving linear program, the simplex method, was motivated by this fact. It works with a set of variables whose number is the same number variables as there are equations. All the other variables are set to 0. Now, back to our actual model. We have some equations that model for us level debt service, but we haven't said anything about how much debt we want. So we add an additional equation which sums up the principal in each of the 3 years to be $100 million. Now think about it. If you didn't have a target amount here, you could have any size level debt service, really. But in particular, most deals will have a target size. So for our example, we're doing $100 million, hence summing up x1 plus x2 plus x3, all the principal, to be $100 million. And of course, let's not forget the all-important objective that we spent so much time talking about before. Our goal here is to minimize that level, because that will correspond to a lower cost for the issuer. So what we're doing, our objective function now is, in a notation we haven't seen yet, is to minimize the variable L.
So that C transpose X that we saw on the prior slide, in this case, it's just going to be L, which is curious because it looks like L is both a variable in our problem, but also it's the objective function that we're trying to minimize. Is that right?
It is just a slightly different notation that's pretty common in linear programming. When the objective function doesn't involve a lot of variables, in this case just involves the one variable L, it's a common shorthand to just show the variable there and not necessarily show, here's the vector C, this is what it equals, and let's write down C transpose times the whole list of variables.
Got it.
And let's also not forget that principal can't be negative. If you really wanted to minimize your level with what we had before, you just have a very negative principal. Of course, there's no such thing as negative principal, so we're going to restrict each of the principal variables to be greater or equal to 0. All right, so now that we've got a conceptual understanding of what the linear program is in terms of equations, let's put that in matrix form. So the left-hand side of the equations that we saw before, we can put into this matrix where each column represents the coefficients of the variables that we saw before. So in terms of the matrix notation we saw earlier, we have our AEQ matrix, and that's multiplied times our x vector. Now, x in this case means the collection of all the variables ordered in the same way that the columns that the A matrix is in. Now, to get the equality, we also need the right-hand side. What's that? And that's simply the right-hand side of the equations we had before turned into a column vector, and that's going to be BEQ. Now, to get to a full linear program, we need a little more than just the constraints, the AX equals B. We also need the objective, which stays the same the way we've notated it here, and a vector or matrix form of the bounds, the lower bounds on the variables.
So we're minimizing our level, which is going to represent the debt service that we've got in each year, and we're constraining the solution so that all of the elements of the x vector are positive, greater than 0.
Correct.
Which makes sense to me. All right, so we've got this laid out in some sort of matrix form. How do we get to some actual calculations to solve this problem? What's our x vector, and what are those actual amounts?
Well, Peter, what we are going for, like you said, we're trying to solve this problem. Previously, in a previous video, we were just solving linear equations. Now we have a full linear program, and that requires an algorithm, and preferably computer code to do it, because this stuff is not something you do by pencil and paper, Peter. So to show you how you can solve this with what's called a linear program solver, we can go over to MATLAB, which does have a linear program solver that comes with the optimization toolbox for MATLAB, and that's called LinProg. What we have here is MATLAB, 2 windows for MATLAB. Above is the MATLAB editor, where we have some code ready to go, and below is the MATLAB console or interpreter. And we're going to step through some of that code above and see the results below. So the first thing we have here, we have the target size of $100 million, and we have a submatrix, if you will, of the big A matrix, and that's just the coefficients that define debt service when you multiply it times its principal vector.
Makes sense. I think this is stuff we covered in those earlier videos.
So moving along, there's a couple of other pieces. We built up the linear program in pieces, so we're doing the same here in MATLAB. We have the L column, and we have the right-hand side. Note the L is not negated yet. It was minus L. We'll do that later. Then we also build up the so-called sources and uses row, which in this case, all it does is assure that the principal adds up to the target size. So we have the sum of the 3 principal amounts. Again, if you multiply this matrix, ASU, against the vector of principals, you'd end up with the sum of the principals. And the right-hand side of that last equation we saw earlier was just the target size. So when we put it all together, with a matrix concatenation in MATLAB, we get back our A matrix that we saw a moment ago and the right-hand side.
Makes sense.
All right, let's not forget the objective. Remember, the objective only had a coefficient of 1 for the L variable. So we have this column vector with a 0, 0, 0, and then a 1. And another thing you can mention, again, thinking in terms of matrix multiplication, if you multiplied this vector C transpose to get the dimensions right for standard matrix multiplication against your X vector, you get back the level. And that's what we're trying to minimize. It's the level. Because remember, the level is the last variable. So when you do that multiplication, all the other ones that get knocked out by zeros, all you have left over is L.
Right.
Finally, the last little bit of setup we have is the bounds on the variables. Recall that all the variables are bounded below by 0, and in practice they have no upper bound. MATLAB has a way of notating that with infinity. Good so far, Peter?
Yeah, so it looks like we're just setting up each of the inputs into the linprog function that MATLAB has for solving the linear set of equations, right?
Exactly. So linprog takes certain parameters, the first being the objective, so we put C here. And the next two parameters it takes are an A matrix for inequalities and a right-hand side for inequalities. But since we have only equalities, we'll tell MATLAB we don't need those by using an empty set for each of those arguments. Following those two empty sets, we have the A matrix for equalities that we just constructed and its right-hand side, as well as the lower and upper bounds on variables, and just a note to the linprog solver to display some iteration information. Note, you MATLAB jockeys out there, we've surrounded the call to linprog with a tick and a talk, which, in effect, will just tell us how long it takes to calculate.
All right, let's let it rip.
All right, let's sit back and wait a while, because it's going to take, it took less than a second.
Wow, it took less than 100th of a second.
Yeah, it was really fast. It's a small linear program, it's not unexpected, but even larger linear programs aren't necessarily going to take a long time.
Right, so our x returned 4 values. The first 3 of those values, are those the principal amounts?
That's right. So let's write that down, in fact, Peter. We'll say that the principal is the first x through the second to last. So there's our principal amounts. And the level, therefore, is the last element of that vector x. And let's check on the debt service. Let's make sure it's level. How about that?
Sounds good.
Remember, we built up this ADS just for this purpose. We said that if we multiplied ADS times the principal, we should get out the debt service. So let's do that. And wouldn't you know it, the debt service is level. It's the same in every period.
It's the same in every period, and it's also equal to that last element of our matrix.
We should also add up the principal to make sure that it really gets to 100 million. MATLAB's got a sum command. There you go, it adds up to 100 million.
On the button. All right, so we've sized a level debt service structure adding up to 100 million using a linear program solver. I think that was the objective, pun intended, of the second item in our agenda here today.
Yeah, before we move on, Peter, how about we show them a graph of the principal and interest?
Yeah, that makes sense.
So we can visually verify also that all the debt service is level. There you have it.
So, right, this looks like principal in the dark green each year and interest in the lighter green. That's obviously getting to a point where debt service itself, principal plus interest, is equal in each year.
You got it, Peter.
Looks good. So that's your 3-year deal. Anyone else structuring out there a $100 million deal over 3 years? You can use this solution without attribution. All right, so what about a more industrial strength problem? I mean, can you really use this in a setting that's more real world?
Sure, so this is really a small example of a linear program and a small example also of a bond structuring problem. When you get to much more complicated bond structuring problems like refundings that involve different modes of debt, it can get much, much bigger. So let's take a look at an example.
Wow, that's quite an A matrix.
Yep, that's an A matrix with almost 12,000 non-zero entries. I think in the example we were working with, there was something on the order of maybe 10 or 12, something like that. Yeah, these problems do scale up pretty quickly.
And in looking at this, I mean, you can see that there's sort of an upper triangular part of the matrix, which I assume is not unlike the small version of our upper triangular three-element matrix for a debt service, that is. But why are there these individual elements that are going diagonally all the way down? What are those?
What we're looking at here, Peter, was a fairly complicated refunding problem where the issuer had a mix of existing debt that was current interest bonds. They also had some cabs, and they had some deferred interest bonds as well. And the refunding was going to include possibly some combination of new current interest bonds, new cabs, and new deferred interest bonds, or converters, if you will. So those upper triangular sections that you're seeing correspond to current interest bonds, just like what we saw in our 3-bond example. The purely diagonal sections, those represent cabs, because cabs only pay at maturity. They don't pay beforehand. And the sections you see that look like they're starting from the left, like a cab, going down a few rows, like a diagonal, and then end up as an upper triangular submatrix, those are the converter bonds. If you had a converter bond that matured before the conversion date, it would behave just like a cab. But if it matures after the conversion date, after that date in particular, it starts behaving like a current interest bond.
Interesting. Well, I'm waiting for the section of the Museum of Modern Art, which ultimately starts displaying bond structuring problems like this. Maybe some different colors, but
We're in the wrong line of work, Peter.
it's definitely artistic. And so in this type of structuring problem, you've got the new bonds in here. It looks like you have the existing bonds as well. But what else can you solve for within this type of construction? Was this a level debt service solution? Was this just like our simple example with the 3 years?
No, this was an issuer that was in a bit of distress. They had some very pressing short-term cash flow needs. They were engaging in what one might call scoop and chuck.
The popular pitch and toss scoop and chuck solution. Yes.
Exactly. They're digging out some of their cash flow obligations now and tossing them out later, hence the preference for cabs and converters. Try to eliminate any interest thrown back by the new issue.
Okay.
And so you can see on the left part of this large matrix, it's a little more ragged because that represents their existing debt, which wasn't issued at the same time as the new debt. So you're catching it sort of midstream. That's why it doesn't look quite as even. But to answer your original question, yes, since it's a refunding, you're solving for more than just the new debt. This is the sort of thing that our Smart Model Structure product can handle. Structure allows you to solve for how much of the existing bonds you wish to refund. In addition, Structure is sizing and structuring the escrow for you.
So you're sizing the deal, you're coming up with an amortization structure given revenue constraints, for instance, and also selecting refunded bonds within the solution.
Yep, all at once.
Interesting. So you've got new money alternatives from current interest bonds to cabs to deferred interest bonds. You're solving for the refunded bonds, and you're trying to come up with a solution that creates cash flow relief in the early years. So within the optimization, you're selecting from whether to issue more cabs than current interest bonds or some form of deferred interest bond relative to refunding more potentially either non-callable or non-economic bonds in the early years to come up with that savings. That's a hard calculation to come to without an optimization that covers it all, isn't it?
That's right, Peter. We've formulated the constraints in Smart Model Structure to capture all those possible scenarios. And depending on what your objective is, whether it's to minimize present value of debt service or something else, the optimization algorithm will pick from all those possible solutions captured by the constraints and give you the best relative to that objective.
Okay, well, it looks like we've got some work to do to submit this to some art contests, and again, maybe change the coloring a bit. But this is excellent work. Thank you, David. In the next video, we can take a look at how you go about selecting refunded bonds in order to minimize an objective function. And I guess that's the question, is what objective functions make sense with this type of large-scale problem. Look forward to that.
Always happy to talk about optimization, Peter.
Great. All right. Thank you for your time, Dr. David, and thank you for your interest in this video. If you've got questions or comments, please shoot us an email at info@intuitive-analytics.com or give us a ring, 646 202 9446. Have a great day.